Okay, so using GPUs in your application. So I really enjoy programming CUDA, and I'm going to be teaching you all about programming in CUDA. But the first rule to adding GPUs to your application is don't develop your own GPU code. Don't go out and write, lots and lots of CUDA kernels. Why? Because there's lots of really good libraries out there. And a lot of the common operations that you want to do in your application, someone's written a library for that. So just as some examples, and these are all hyperlinks in the slides. cuBLAS has got dense linear algebra primitives. So people here familiar with BLAS? So BLAS is that defined in the 70s? Sorry? 60s. Okay, cracky. Okay, so BLAS is the basic linear algebra subroutines. And this was something that was defined back in the 60s, all Fortran interface for doing basic linear algebra operations like adding two vectors together, or doing matrix-matrix multiplication, or matrix vector multiplication. Because these are one of the most fundamental basic building blocks for many high-performance applications. So someone went and wrote a specific interface API for this. And then whenever someone released a new computer, they would release their own highly optimized implementation of BLAS. And NVIDIA have released their cuBLAS library, which is available for free online. And I saw a talk from an engineer who was working on CUDA compilers the other day. And he said that NVIDIA's BLAS library is full of hand-optimized machine code that no compiler will ever be able to generate. So it doesn't matter how good you are at programming CUDA, you're not going to be able to beat cuBLAS. And I've got a colleague who's working on dense linear algebra, solving big eigenvalue problems in a distributed sense. And he uses cuBLAS for when he has a small matrix chunk to multiply against another small matrix chunk. He uses cuBLAS for that for that operation. Thrust is a library. So if you're familiar with C++ and the standard template library, so it has lots of algorithms like copy and transform and find if. Thrust is an attempt to write an equivalent library from the GPU. And my colleague Thibault will be discussing Thrust on the last day. He'll present some information about that. So it provides some algorithms and some containers for storing information on the GPU. So if you want to do also things like reductions and parallel scans. Random numbers are important, and please don't write your own random number generator. So cuRand is a library provided by NVIDIA, and there's also another really good library called Random123. These are very good random number generators. As a general rule of thumb, you shouldn't try to implement your own random number generator. And so there's good libraries for that. There's a cuFFT, which is what it says on the package, FFT, and Cocos is another example, which is I think it's developed at Sandia National Laboratories in the US, and it's a generic C++ template library and it's got lots of parallel motifs. So data structures and algorithms, and it's designed to be highly portable. So it has a CUDA backend, and it has a multi-core backend, and then it's highly specialized. It will rearrange data differently depending on which backend you are. And it might be all that you need. So before you start hacking, take some time to find out what libraries are available out there. There are lots of libraries, and because GPU is really taking off now, there's lots more libraries coming available every week. But if you really have to write your own code because there's no library, or because also when you're writing stuff with a bunch of libraries, you still need to write a bit of glue code to make everything kind of stick together, or because if you're like me and you just really enjoy it, you can. This is a very general way of speaking. There's two approaches that are becoming popular. One is to use directives. So I already discussed this earlier, where you can add specially formatted comments to your code, and a compiler that knows how to speak OpenACC or OpenMP4 will generate GPU code for you automatically. And in theory, this is the easiest path for porting your code, because you take the application code, maybe you refactor it a bit, then you add some directives, and voila, the compiler has made your application run on the GPU. And for some applications, this actually works. I mean, if you have the sorts of algorithmic motifs in your application that the compiler is able to recognize and generate code for, it works very nicely. So if you're doing, for example, stencil operations, then this can work very well. But you might find that if you have to start doing more and more complicated things, like for example, anything that involves doing like an inclusive or exclusive scan operation, it can get much more difficult, much faster. And you might still have to go to a GPU-specific language. So these are languages that are designed specifically for GPU programming, and they give you the maximum flexibility and performance. So CUDA is a good example of that. Also OpenCL. OpenCL feels very similar to CUDA in a lot of ways. Of course, OpenCL is designed also to generate code that will run well on multi-core vectorizing processors, but it's not so well supported by NVIDIA or Intel, unfortunately. So we're stuck with CUDA on NVIDIA GPUs, and the nice thing about CUDA is that it's designed to run on NVIDIA GPUs, so it gives you full control over the platform. So before you start working on a GPU implementation, it really does pay to sit down and have a think about whether it's going to be worth it for you to support GPUs. So, and there's some questions you might want to ask. And the first one, is my program computationally or bandwidth intensive? And the reason we want to ask that is because GPUs, their real performance benefit is that they can do an awful lot of computation, and they've got very high memory bandwidth compared to a normal CPU. So if you have an application that is really, when you look at how fast it has, what's stopping it from going any faster, if it's computational throughput or memory throughput, then a GPU might actually be able to help you. And does it have enough parallel work to utilize the GPU? So if it's an application that has to do lots of computational work, but all you've got is a sequential single-threaded algorithm, then, or you can't actually find much parallelism, then you won't be able to use all the resources on the GPU. And we're going to see later on that you actually have to have an awful lot of parallel work before the GPU starts to be competitive against a normal CPU. And are there any serial, the next question is, are there any serial bottlenecks that will limit scaling? Because we will have problems if 10% of the application is serial, and eventually you won't, or if 10% of an algorithm is serial, you're going to get some pretty severe limitations on how much you can scale. And finally, is the pain worth the gain? So you might look at this and say, my application, and we see this quite often, people say, I want to run on the GPUs, and then if they actually do some analysis, they might say, oh, well, actually, my application isn't really suitable for running on the GPU. Other people might say, well, it is suitable, I think, if we put a lot of work into the code, but it isn't actually that important to us that we get that much faster. Because you might say, we need to do a lot of work on our application to make it run on the GPU, and then you have to answer the question, well, what's the trade-off between time invested in development and getting the improved performance? So questions 1, 2, and 3, we're going to address those in this course. I'm going to quickly mention have a look at question number 4 now. And basically, to answer question 5, you need to have answered the other 4 questions first. Basically, understand your application before you decide whether or not to use the GPU. So there are some limitations to parallel speedup. Who here has heard about Amdahl's law? So Amdahl was an engineer at IBM, I believe, and he came up with this pretty simple law, and it's about the amount of parallel speedup you can get from an application or from an algorithm is limited by how much of the application must be executed in serial, or the proportion of the part of your application that is serial. So when I say serial, I mean not parallel. It can't be done in parallel. And Armadale's law basically gives you the maximum possible speed up. So it gives you the best possible speed up you could expect when only parts of your code can be parallelized. So if we assume that the parts of the code that can be parallelized perfectly, what are we going to get? And it's the time for n parallel processes is this, the time for one parallel process, and p is the proportion between 0 and 1. That is serial. So if p is equal to 0, then basically if p is equal to 0, then the entire application is parallel. And if p is equal to 1, then the application is entirely serial. And if we take the limit as n tends to infinity, we get that the time to solution for n processes is p times t1. And this has a surprising effect, because you might think only 0.2% of my application is serial. Therefore, I'm golden. I'm going to get lots of parallel scaling out of that. But if you plot the so this is a plot here of the best possible speed up you could expect to get, and so each one of these lines here is how much of the application is running in parallel. So 99% means that 99% of the application could be written in parallel, and it could be written in a parallel way, and only 1% of the application was serial and had to be done, couldn't be done in parallel. And you see, you very quickly, even for 99%, you very quickly run out of scaling. So you've got to be very careful when you're looking at application, because when we're looking at GPUs, we're looking at scaling up to thousands of threads. So we've got to be, so it's a very good exercise to go through and have a look at your application and look at what are the serial bottlenecks. If your application's already running in a highly distributed way on using MPI, then you're probably good, but this is worth keeping in mind. So we're going to be learning about CUDA. So CUDA is a pretty big thing. If you go onto the NVIDIA's CUDA website, they give you all these marketing terms about it being a big platform, and it's all sorts of things. It's specifically for running, for doing, it's a computing platform and an API for working on CUDA-enabled NVIDIA GPUs. And it includes multiple languages, CUDA C++, CUDA Fortran, there's a CUDA Python. It includes lots of different ways to use and run on the GPU. But usually, or often, when people talk about CUDA, they're talking about CUDA C++, which is a specific programming language, which was the first language that was available for programming CUDA, and is still the main one. And the runtime API, the runtime application programming interface that comes with that. So CUDA C++ is a superset of C++. That is, it is C++ with some extra stuff put on it, with some extra extensions. And so you can take a normal C++ program, you can write your little hello world C++ program and compile it with the CUDA compiler and then run it, and it will look just like if you'd compiled with your normal C++ compiler. It will just run on the CPU, the hello world program. But CUDA C++ adds additional instructions, syntax, for defining work that you want to run on the, for defining work functions, basically, or what we call kernels, that you want to run on the GPU, and additional syntax for launching those kernels. So once you've defined something that you want to run on the GPU, you can then, it provides a syntax for launching that work on the GPU when you want from the main application. So but you can think of it as C++ with some extra features added on. And the CUDA toolkit is more than just the programming language. It's got the runtime API for managing GPU resources and execution. So if you want to allocate memory on the GPU, or if you want to run multiple GPU kernels at the same time on the multiple GPU workloads on the same GPU, it provides a set of function calls that you can make to synchronize and organize all of these things. And it also has a bunch of tools, including profilers. So you can just run your application in the profiler to understand where its performance bottlenecks are, and debuggers
and also got a memory debugger. And we're going to look at some of these throughout the course. So now we're going to just have a quick look at how to compile CUDA. All the exercises in this course have got make files, but I think it's useful to have a little exercise at the start where we actually call the NVIDIA compiler to compile something, and also so that everybody gets a chance to log onto the system and check that everything's working for them. So CUDA code is compiled with the NVCC compiler driver. So normally when you're compiling C++, you'll use G++ or Clang or whatever. For compiling CUDA, we use NVCC, and the source files usually have a .cu extension. So instead of .c or .cpp, they have a .cu extension. And header files, there's no real standard way of doing the header files that I've seen. Sometimes they've got just a .h or a HPP, and even sometimes I've seen a .hcu. But it's important that you use a .cu extension. So CUDA compilation involves multiple splitting, compilation, pre-processing, and merging steps. It's actually pretty complicated what NVCC does, because it takes your input source code and then it splits it into two parts. The first part is the part that's just going to get compiled by GCC, your standard CPU compiler, C++ code. And then the other part is the GPU specific, the little bits of code that had to get compiled for the GPU. And then it passes the CPU stuff over to the GCC, and then it uses its own compiler, GPU compiler, to generate the CUDA, the GPU code. And then at the end, it joins everything back together. So it's quite complicated, and if you're lucky, you'll never have to look at how it works under the hood, because an NVCC hides this complexity from the user. It closely mimics the interface to the GNU compiler, so a lot of the flags are the same. And so as I said, yeah, behind the scenes it does these different splitting and merging steps. So here's an example of compiling some CUDA called NVCC, and then there's a bunch of flags here. So these first two flags are flags specifically about generating the CUDA code. So the -arch equals SM60, that's telling it, I want you to generate code for the Pascal P100 GPU. If you wanted to generate for Kepler, the previous generation, it would be SM35. So, and if you've compiled stuff for a processor before, you might have done something like -march equals AVX. Well, this is the equivalent for the GPU. Minus line info is equivalent to -g. It's putting in some, it basically inserts extra information about line numbers into the generated code so that when you use a debugger, you can get that information out. Then it has this flag here, the -g. This is for the host code. So host, when we talk about the host, we're talking about the CPU. When we talk about the device, we're talking about the GPU, because the old model was you had a GPU, and it still is on our system, you had a GPU which was attached by the PCI bus, and it needs to have a processor, a host processor that actually runs it and drives the application. So the host is always shorthand for the CPU, and the device is the GPU. So we have one flag that's going specifically to the host, that's -g, to just generate some debug information. And then we've got three of these flags which are kind of applicable to both. We've got -02, which is the optimization level. So this is saying optimize. When you say what optimization level you want, it's the same optimization level for both. -standard equals C++11, so you can tell it which version of the language you want to use, and the output for the name of the executable. So does anyone have any questions about that?
Is it possible to use, for example, Intel compilers instead of GCC?
I don't think you can use the Intel compiler. If you're in Microsoft land, you can use the Microsoft Visual Studio compiler, and I believe they've also got support for the PGI compiler. But I don't think they have support for the Intel compiler. They've got checks in the header files that actually check if you're compiling with Intel and throw an error. And you used to be able to just comment out those, make a copy of the standard library and comment out those checks. And it used to work. But the problem is that because it does this, splitting and merging, it's heavily, the CUDA compiler is heavily dependent on GCC and non-standard extensions. So I don't think you can use the Intel compiler. But what you can do is, of course, you can write normal C++ code and compile that using the Intel compiler and link that against your CUDA code. Or you can compile your CUDA separately and link that in. That's not a problem. And that's the way we usually work around things like that.
So can you swap, for instance, the version of GCC on your system, and does the CUDA compiler just use that?
Yeah, so it'll look, there's some standard places where it'll just pick up whatever's in your path, usually. But you can, if you have a specific version of GCC installed somewhere that you want it to use, there's a flag -ccbin. There's a flag where you can say, I want you to use this compiler and this standard library, and yeah. You've got a lot of control over that sort of stuff. So now we're going to do a little exercise. We're just going to basically log on to Piz Daint and then do a git clone to get a hold of our the training material. And then we're going to compile a hello world example. Not very interesting, but the purpose of this, and we're going to compile it using NVCC, the purpose of this is to let you have the opportunity to just make sure that you can log on and do any debugging of that process before we get on to the more interesting exercises later on. And I've just noticed that I made a mistake, so I'm just going to update. Oh, I almost sat on this.
I don't have a password.
Okay. Okay, so do we have any, we handed around those little bits of paper with the usernames and passwords on them. Do we have some left over? Okay. Okay, so I've just I've updated this to add this line here, module load CUDA toolkit GCC. So I'm assuming that everybody has a terminal application and they know how to use a terminal to log on somewhere. So open up the terminal and then SSH onto Piz Daint. So you will have, on your piece of paper, you'll have course and a number and then your username. Just use whatever the number was there, so course 23 or course 12, whatever, @Daint. So the next step will be to get one node on the course reservation. So when you run this command here, the salloc command, what the salloc command, we pass the -c GPU, which is saying I want to get an allocation on the GPU part of the system, because we've got two parts. We've got the multi-core and the GPU part. And then you need to give reservations. So we have a reservation, which is called Pascal 1 day. Tomorrow it's going to be Pascal 2 day, and the day after Pascal 3 day. So when you run salloc like that, it's basically going to give you a node. And then later on, you can use this srun command here. Once you compile your code, srun will then take your code and run it on that node.
Sorry.
So yes.
I don't think I can get the node, and I'm not sure what I'm doing. Maybe it's if it's
The project course is either specified.
I hope I'm running the command correctly, honestly.
Okay. Just let me. I'll try. So. Sorry. More of these sheets. Yeah, you don't have the magic CSCS stuff account. Yeah. Okay, so I've got some people saying that they're having trouble getting a hold of the thing. So let's do some debugging. So. Okay, so I've just logged onto Daint. Okay, so now my job is to find out what's going on. So salloc. Okay, so this is a list. So Pascal 1 day starts at 9 o'clock and ends at 5 o'clock today. Salloc minus reservation equals. By the way, this is to be expected. This is why we're doing this little test now. Minus C GPU. Was anybody able to get? Did this work for anybody? So for the course account, so it's the group, huh? Let's see. So Pascal 1 day is the courses. So it would appear that they probably didn't add the people to the courses group.
But also for CSCS, it's not working.
Sorry?
Also for the CSCS stuff, that's not working.
Yeah. So, because sometimes it takes, when you ask for a node, sometimes it can take a little while to give you the node, but this is taking longer than it should. So just to reiterate, this isn't really a problem because I put this here so that we would sort out these problems. They often happen. I might, we might just leave this and get on with the next bit of teaching. That's a pity. Or I could run up and try to get someone to.
If you like, I can go up.
Yeah, can you get up and just? It'll be one of the guys. I think Vincenzo. It was Vincenzo who did the reservation. Okay, so. So we can keep on doing the exercise. We just won't be able to, and we'll be able to still do the git clone and get the code and build the code. We just won't be able to run it. So if we look at the slides, if you look at the slides here, this here gets us the node, this salloc call, and this call to srun down here will actually take our nice little GPU code that we've compiled and run it on the GPU. But all of the rest of the stuff here we can do. So you can log on, and then you can go to the Scratch directory. So Scratch is a special file system mounted on Piz Daint. And when you want to run your application on Piz Daint, you have to run it from Scratch. So it's important that you change to Scratch. $Scratch, that's a shorthand environment variable that will have been set for you that has the directory for your Scratch. And then you can do a git clone of this address to get a copy of the all the training material. Now, is there anyone here who's not really comfortable with using terminal, logging on, doing that sort of stuff? Because now's the time we can help you get that sorted out. It's also important that you keep your bit of paper with your user account name on it and don't change from day to day, because when you go to, if you want to use the work tomorrow that you did today, it'll be stored on the Scratch path associated with your account. So if you change to a different account tomorrow, you'll lose whatever work you did today. Okay, so I have logged on. Can people see that? Is it for the people at the back? Can everybody see this line down here? People at the back? It's good? Okay. Tell me if you want me to make the font bigger. I'll make it a bit bigger now. And I'll put myself up the top. Okay, so first thing I have to do is go to Scratch. So I just hit Tab there. So you see it's taking me to my own personal path. Yours will have, /course something. Okay. And then I want to do the git clone. I'm just going to Okay, so now I'm going to clone the repository. Are people here familiar with Git? Or is there anyone who's not familiar with Git? We don't need to be Git experts to do this course, but what that has done is that's gone and downloaded the source code and teaching materials for this course, and it's put them into a directory called Pascal Training. And if we look at what's in here, we can see that we've got a slides directory with the slides, and then a bunch of directories with some different exercises, different source code in them that we're going to use for the exercises. For this little exercise, we're going to go to Demos, and we can see that we have a make file here, but we're going to work on this hello.cu code. Let's have a look what's in this. This is just a hello world. So it's very simple, and we're going to learn, by the end of this course, you'll understand everything in here, plus lots more. But at the top, we've got something called a hello kernel that's going to print out a message. And from looking at it, you can probably guess what it's going to print. And then we have a main function here. So let's try to compile it. Well, first, is everybody up to this stage? Ah, sure. Sorry. I will do that for you now. So module load, because if I look at what version of GCC have I got, we've got the default version that comes with the system, which is 4.8.5, which isn't very recent. And if I try to run NVCC, I get an error saying that it's not here. So we use things called modules on Piz Daint to load up different software packages. So if we module load CUDA toolkit, okay, so this has now loaded up all of the CUDA related stuff. So if I go nvcc ---- version, okay, good. So now we've got the NVIDIA CUDA compiler driver version 8. And now we should have a more recent version of GCC, GCC version 5.3. And you can do those all on one line. So you can just say module load CUDA toolkit GCC if you want. And for all of the exercises, except for the MPI one, this is all you'll need. For the MPI one, we're going to need to load up the MPI compiler wrappers and all that sort of stuff. But, yeah. So to compile our code, nvcc so we're going to target the Pascal architecture. This is a very simple application. There's no reason to use a Pascal for this, but there you go. It's a good habit to get into. I don't think I even need to do that, do I? Hello.cu. So I'm calling the compiler wrapper. I'm telling it which architecture to target, which file to compile, and then the name that I would like for the source code, for the thing it generates. And now it's generated this hello. Now if I try to run hello like this, I'm going to get an error because right now I'm logged on to, I'm in one of the login nodes, which has just got some normal CPUs on it. It definitely doesn't have any CUDA-enabled GPUs attached to it. So when I try to run the application, I get this error message saying I can't find any GPUs. If we wanted to run it, we actually need to get a hold of a compute node that has a GPU and launch the job, launch the executable on that node. And have we got any feedback about?
Yes, we have to add a partition flag, so -p, then Jalad, and then it should work. So I can show you.
Can you just write it down, and I will update the slides. They changed, when they upgraded the system recently, they changed how all of this stuff is done, so excuse me for not being...
Oops,
this right?
so we have to add this -p Jalad.
J-A-L-E-T.
And then it works. I tested at least for the CSCS account.
Okay. Okay, so Marcel, I'll put that on the slides. So so apparently it's just one additional flag that we need to set up. Maybe I can quickly update the slides, huh? So it's minus p equals jarlet?
But it's a lowercase p.
Okay. Like that? It works? Okay. Okay, so I'm just going to copy that. Yeah, what sort of, who uses LaTeX to do this sort of stuff? Okay, so we have added an extra flag, minus p jarlet. I don't know what that means. It's probably a mountain somewhere in Switzerland, right?
Sorry, one question. Do I need to have a course account, or can I use my personal CSCS account?
No, you can't use your personal CSCS account because this reservation there's only a certain groups that are allowed to run. Oh, one of those bits of paper? Sure. I mean, of course, you can use your personal account, but then you would have to run it using your groups. Okay, your professor might not be so happy. So I'm going to actually write this on the board. So have people been able to get their allocation and run? Where am I looking at? So put your hand up if you've been able to successfully get a node and, okay, so that's just me. And did you run it? Yep, aha, here we go. Okay, so srun will launch our job, and if you're running an MPI application, you can pass in flags to say how many nodes and how you want the MPI configured, but for us, we're just running a single little job. And it printed hello world from a NVIDIA GPU, which is really bad for performance. You never want to do printf from a CUDA kernel. So has anybody not been able to reproduce that? Because I'm quite happy to take the time to make sure that everybody can do this, because we're going to be doing lots of exercises, so it's good to have everybody ready to go and debugged. Okay.